Es bueno? It's good? Okay. Now, let's see here. When did I start? I started at, I think I started an hour. Yeah, straight up an hour ago. So I have like 15 minutes left here. Okay, so I'm going to state some things without proof here, I think, in the last story arc of today, and we'll come back and prove some of them next time, okay? So what are theorems that we know that we should prove like next time? Theorem. One of the theorems we know is that if H is a subgroup of G, right, and the order of G is less than infinity, then the order of H divides the order of G. This is called Lagrange's theorem, right? This is actually proved in Stillwell, and I'll hopefully cover the proof of that next class, okay? This is Lagrange's theorem. So what's an application of this? By the way, definition. The order of A is equal to the order of the set generated by A for A in a group. That's actually not the definition. My bad. What was the definition of the order of A? Actually, the definition, this is actually a theorem. My bad, this is a theorem. You could take that as the definition, but the actual definition for the order of an element is what? The order of A is equal to n in the integers, in the positive integers, for which a to the power n is equal to 1, all right? But a to the n minus 1 is not equal to 1. So it's the least positive power that when you raise the element to that power, you get back to the identity. Now, this doesn't have to happen, right? There are infinite groups where you have the order of A. If no such n exists, then we say what? Then we say that the order of A is equal to infinity, all right? So with respect to that definition of the order of an element, there's a theorem. You can prove that the order of the element is equal to the order, which is to say the size of the subgroup which is generated by A. All right? So if you know this theorem and you know Lagrange's theorem, what does it tell you about the order of an element? Sort of a corollary here, right? If the order of G is equal to n, and A is an element of G, then the order of A is what? Is a divisor of the order of G. It divides the order of G. Let me sort of give you an application of this, right? In Z500, there does not exist an element x with the order of x equal to 11. Because if the order of x is equal to 11, then the set generated by x subset has order 11, And the subgroup generated by X is a subgroup of Z500, right? So by Lagrange's theorem, this implies that 11, the order of this is dividing the order of Z500. Well, the order of Z500 is 500, right? Which is to say that 11 divides 500, which is not a truth that you can buy in the store, right? I mean, you need to like redefine the meaning of numbers to get that one to work. You have to change the meaning of 11,500 for that to be true. On the other hand, right, if I asked you, does there exist an element of order 50 in Z500?
Yeah.
Right?
They divide.
Yeah. Then it seems like it's possible, right? Actually, we don't have the theorem in front of us yet that says it has to happen.
Yeah.
But actually, there is. All right? Let me tell you the let's see here. All right, so if, oh, and also there's another definition I haven't stated yet. Definition. If there exists A in G such that G is equal to the set generated by A, then what do we say? Then G is a cyclic group with generator A, right? So, okay, if A is a generator of G, what else is a generator of G? Well, another theorem you can prove, all right? And we'll prove all of these that we find time for next time, and as your interest, takes us, right?
Yeah.
All of the things I'm saying are well within our grasp to prove, for sure. All right, there's nothing harder here than anything we've done up to this point, for sure. But another thing you can prove is this theorem. If G is equal to the set generated by A, and, all right, the order of G, right, is less than infinity, so it's a finite group, all right, then
Keep going. I gotta take a call. I'm sorry.
G is also equal to the set generated by A to the power K, where I need to say that the order of G is n, the greatest common divisor of n and k is 1. So let me put it into words. Any relatively prime to n power of A is also going to serve as a generator for the group. All right, let's see here. So application. If G is equal to the set generated by A, and let's say that the order of G is 10, right? Then let's see here. 1, not 2, 3, not 4 because 4 is a common factor of 2. Let's see here. 1, 2, 3, 4 is out, 5 is out, 6 has got a common factor of 2, 7. 8's out because it's got a common factor of 2. 9 and 10 are relatively prime. So then these are relatively prime. Relatively prime to n equals to 10. Thus, G is also equal to the set generated by a cubed. It's the set generated by a to the 7th. It's the set generated by a to the 9th. All right. So this theorem is very useful if we're trying to understand what are the different ways we could generate a set. So let me put a corollary here. We could count. So corollary. The number of generators for G cyclic, right? With the order of G. Well, we could just say this rather than introducing an n, is the Euler phi function of the order of G. Uh-oh. He's gotten locked out. Oh, no. Oh, you already got around, huh? I was going to open the door for you.
I am a runner.
You are a runner, yeah.
Sorry, that's a ball.
That's okay. Don't worry. I can talk to myself just fine. It's one of my many skills. So what I'm saying is that if you want to find other generators of a cyclic group, any relatively prime power, relatively prime to the order of the group power, will also give you another generator. So like if the order of G is 10, 3, 7, and 9 are numbers which are relatively prime to 10. And so that means a cubed, a to the 7th, a to the 9th. These are alternative generators for the group. Another way to look at this is if the group has order n, it always has phi n generators. You have a few homework problems that are based on this counting. Okay? Like, for example, here's another application just before I leave this. If H is a subgroup of G and the order of H is equal to 8, then there exists phi of 8, which is equal to 4 generators in H. And I do mean to say, I'm sorry, I need to say cyclic. If H is not cyclic, you can't generate it with one generator. Yeah. Not every group is cyclic, all right? Not every group is cyclic. Certainly not. So let me try to say the remaining big ideas. You remember the direct product of groups? Okay. Well, I guess, let's see here. Let me finish actually this one. So here's the theorem. And I guess some people would call this the fundamental theorem of cyclic groups. I don't know. Fundamental theorem of cyclic groups, which is that if G is cyclic with order n, and if, let's say, K divides n, then there exists a unique subgroup of order k in G. Moreover, every subgroup of a cyclic group is cyclic. So that's a kind of a converse to Lagrange's theorem. That's not true for general groups, but it's true for cyclic groups. If 3 is a divisor of the order of your group and you have a cyclic group, there is a subgroup of order 3. If 3 is a divisor, I shouldn't use 3, that might be too low a number, I may run into special case stuff here. But anyway, like pick, if, I don't know enough group theory to say something cogently here, but pardon my ignorance, if 20 is a divisor of your, abstract, not possibly non-abelian group, all right, it doesn't follow that there exists a subgroup of order 20. There may or may not be a subgroup of order 20 if 20 is a divisor of a non-cyclic group. But for a cyclic group, indeed, there is a subgroup of order k, and more than that, I can give you a formula for it. See, if G is equal to A, right, then the H I'm talking about is equal to the subgroup generated by A to the n over k. Remember, k is a divisor of n, so n over k is an integer. So like, and in additive notation, this is even simpler, right? Like, almost done here. So this is, your question was like, what are the subgroups of, say, well, for example, Z20, right? Z20 has, which of course you could write as generated by 1. What else could it, what are its other generators?
20.
20. Now we didn't talk about 20 yet.
5.
But here's the theorem. If m and n are coprime, then phi of mn is equal to phi of m times phi of n. So that's a theorem we'll prove next time. The reason that's true is because, like, u mn is actually isomorphic to u of m, Cartesian product with u of n. This is the direct product of groups. So we'll have to get into that next time. We need to talk about isomorphism. We need to talk about direct product of groups and such. So anyway, this one here. So what are the other generators? I mean, so phi of 20, how many are there?
2.
Well, it should be phi of 5 times phi of 4, right?
Yeah.
Phi of 5 is 4 because 5 is prime. Phi of 4, I think we said was 2, so there are 8 generators in here. There's 8 other things you could put here, right? But what are the divisors of 20?
1, 2, 4, 5, 10,
20, right? Those are the divisors. And so, let's see here. So here n equals 20, right? So my claim is that 20 over 1 and 20 over 2 and 20 over 4 and 20 over 5 and 20 over 10 and 20 over 20, these are all subgroups of Z20. And those are all the subgroups of Z20, right? So the 8 generators. So this one has 1. I mean, of course, this is literally just Z20, right? This one is the set generated by 2. So this is 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, right? That has order 10. Order 10. See, the set generated by 20 divided by 10 has order 10, as I was indicating. Oh, my bad. I seem to. Oh, no, I am there. And what's this one? This is the one, this is kind of a silly one, right? This is stupid. This is just the trivial additive, right? So let's see here. This one, of course, is the set generated by 10, which is 0 and 10, right? This one is got 0, 5, 10, 15. And this one has got your multiples of 4.
Why don't they go to 20? Is it because
Order 1, order 2, order 4, order 5, order 10, order 20. What's that?
why doesn't it go to 20?
Why doesn't it go to 20?
Is it because it's Z mod?
Well, I'm using 0 to 19 as representatives.
Okay. But,
Um,
okay. Oh, so you can just change the representative and then you change the.
Oh, yeah. But the numbering would be the same here, right? Now, then we can start to ask more interesting questions like, all right, so what are these subgroups isomorphic to? Right? Well, these are cyclic. Each one of these is a cyclic subgroup. And up to isomorphism, there is a unique subgroup, a unique cyclic group of order, whatever.
Oh, so you're saying 10 and 4 would have subgroups too, since they're.
Well, what I'm saying is because this is a cyclic subgroup with 2 things in it,
Yeah.
this is isomorphic to Z mod 2.
Yeah. And that gives you 6. And then what about 4?
This is isomorphic to Z4.
Yeah.
This literally is Z20, but now, so bringing back to a question I alluded to earlier, one of the questions we need to answer next time is, what about UN? Is it cyclic? You know, is UN a cyclic group? And the answer is sometimes. But generally, since UN is an abelian group, the fundamental theorem of finitely generated abelian groups is that any abelian group can be written as a direct product of copies of Zn up to isomorphism. All right, so that's one of the other things I should share with you guys next time. But I think that's a good place for me to allude to, but not right on the board today. I'm just going to kind of stop there. So let's see, what I have left to talk about is like the theorems about like orders of how orders of elements have to divide the order of the groups, some things about that I haven't written explicitly. But I hope this is enough to get you started down the path of doing my groupy homework. Yeah. And mostly I just wanted to review this stuff with you guys because I know it's kind of the end of the semester a little bit, and you know, these are things you'd like to know before you take like the subject GRE, things like that. Or before you take a graduate course in abstract algebra, right? I mean, you need to have